Another technique to improve the estimate of the area under the curve is to use trapezoids instead of rectangles. So we do something called a trapezoidal approximation, or sometimes it's called the trapezoidal rule. All right, so how that works is that for me, I usually work this out visually there are ways to set up a table for it. You could probably really invent your own way, and I have some things to show you about it. But it really starts with a picture. So instead of building rectangles for each segment of delta x, right, I'm going to make a trapezoid, and you can see that that's going to have much less error than any of my rectangle approximations did, because that line's going to follow pretty nicely along that curve. So what I do is I make 4 trapezoids, and the last trapezoid is actually going to be a triangle because one side is 0. All right, so we're going to call these trapezoids T1, T2, T3, and T4. And then we'll just find the area of each of the trapezoids. So we have to remember that the area of a trapezoid is equal to 1/2 the height times base 1 plus base 2. One thing that's a little confusing is you have to think of the trapezoids as being this way, so that this is B2, this is B1, and the height is here. So the height is delta x, actually. All right, see, that's where the trapezoid is. Okay, so the height is delta x, and each of the B1 and B2 are f of x sub I. Right? So this is our B1, and this is B2, and this is h. All right. So then I can really just sort of looking at this picture and maybe thinking about, putting the coordinates to start. Maybe that would help organize it. Here's y equals x squared. I've been using f of x. Now I'm using y. Yeah. All right. So this is the point 1/2, 1/4. This is the point 1, 1. This is the point 3/2, 9/4. And this is 2, 4. And this, of course, is 0, 0. All right, so with the trapezoid, I'm going to build 4 trapezoids. T1 is going to be, so 1/2. The h is the delta x, which is 1/2. By the way, notice it's still true that delta x is equal to b minus a over n, which is 2 minus 0 over 4, which is 1/2. So that still holds for trapezoid rule. All right, and then my B1 and B2, they're really f of x sub 0 and f of x sub 1, if you like. So in general, these are going to be like f of xn and f of xn plus 1 would be one way to think of it, although you certainly don't have to. So one side of this triangle, the height is 0. The other side, the height is 1/4. 0 plus, we say 1/4. All right, so that really collapses because of the 0, just collapses to 1/2 base times height. That equals 1/16. Then for our trapezoid number 2, we have the 1/2 from the formula. We have the 1/2 because h is 1/2 because it's delta x. This height B1 is 1/4 plus this height is 1 because those are the y coordinates. So that's going to turn out to be 5/16. And then for my T3, I get 1/2 from the formula, 1/2 from delta x. My heights are 1 and 9/4, using the y coordinate in each case. These values here, the B1 and B2, are y coordinates from the function. All right, so you can work that out. It's 13/16. And then your T4 is 1/2 times 1/2 plus times 9/4 plus 4, right? 4, yeah. So that equals 25/16. So you can see certain patterns are going to happen. You're always going to have the 1/2. You're always going to have the delta x. And then you're going to have f of x0 plus f of x1, f of x1 plus f of x2, f of x2 plus f of x3, f of x3 plus f of x4. Right? So that's what those are. And then, in practical purposes, just find the area of the trapezoid and add them up. We get 44/16. Same as 2 and 12/16, which is 2 and 3/4, which if you compare them to our previous estimates is very consistent with what we're getting from our other estimates, right? So for our midpoint, we got 2 and 16/27. So these are all in sort of the same ballpark. They're all between 2 and 3. In fact, they're all really between 2.5 and 3. This one was, we had for n equals 8, between 2 and 3/16 and 3 and 3/16. So all of these estimates are comparable, but they're not equal. If we want our value to come out always equal, we need to use whatever shape we use, we need to use infinitely many of them. Now, before we pass to that, I want to show you this, which I have posted on your Google Classroom. It's called Riemann Sum Notes. And what it has is, for each of the left rectangular approximation, right rectangular approximation, it has a graph, it has how you lay the chart out, and it has these nifty formulas that I have not talked about, right? If you think of, the area, let's drop back to this one, right? The area is the sum of f of x sub I delta x, right? Well, you can factor the delta x out of that sum, and then you have this, because you're really factoring that out, factoring it out of each of the terms. And the reason that I wrote these out is people who are interested in computer programming sometimes are interested in a way that you can sort of put this into a formula. So I have a table, we have a graph, can you put it into a formula? This is the formula, these are the formulas you can use. So here's a picture of our midpoint approximation. All right, you have to calculate the midpoints, which are x sub I plus 1 over 2. So you end up with, these are the midpoints, x0 plus x1 over 2. So if you look at our midpoint approximation, how could I have calculated this value as 1/3? Well, it's 0 plus 2/3 divided by 2. It's the average of it's the midpoint of these two, right? 2/3 plus 4/3 is 6/3, which is 2. Divided by 2, I get 1. So the x sub i's that I'm using, I didn't write this out explicitly, but how you get them is x sub I plus 1, whatever x you're on, plus the next one divided by 2, the average of the two x's. All right, and then so there's a chart how you can lay that out. Because of this peculiar formula of getting the average of the two x sub i's, that's why this formula looks like this. All right, and finally, here's one for your trapezoid rule. Here's a nice picture of trapezoid rule, including some negative values. There are ways you can lay out a table and a formula, and I invite you to study that on your own if you find it interesting, if you're interested in writing a computer program for it. Otherwise, our trapezoid rules are generally going to use only, 4 or 5, 3 or 4 really iterations. So you can just lay it out like this, and if you want to get more fancy with it, you can. So this gives you enough information to do the worksheet Riemann sums number 2. That's now assigned as homework. It's only got 2 functions in it, but I'm asking you to do the sum 4 different ways, so there's really 8 problems. So this is significant, all right? You also now know everything you need to know about approximating with finite elements. So the next thing we're going to do is look at how to not approximate, how to get exact values using infinitely many elements. So in a way, these finite methods are just laying the groundwork for the infinite method that we're headed toward, these finite methods like this. They're laying the groundwork for the infinite method we're headed toward. But they also have another important function. We're going to see how we can use infinitely many rectangles by using the limit on certain functions and get exact values for certain functions. But it's going to turn out you can't do that for every function. There are functions that are resistant to analytical approaches. And for those types of functions, and notably e to the negative x squared, which is used in statistics a lot, and you need to find the area under that curve, you have to use an approximating method. So for those functions that don't have analytical solutions, you have to use one of these approximating methods. So it's important to understand them and understand what their various pros and cons are. Also, it's worth noting, though, that using a large enough number of rectangles can get you an arbitrary degree of accuracy. So any degree of accuracy you want, any positive number epsilon that you want to have be your error, you can get by using enough rectangles, you can get within that level of error. So if the limit might exist but not be calculatable. So because the limit exists, though, the calculation can be arbitrarily accurate. All right, so that's enough of that. Next up, we're going to stop talking about it and actually do it.